Good evening. I'm Dario Santonocito. I'm a PhD student from University of Messina. Today I will present you a work entitled Non-Destructive Diagnostic Analysis of Pipelines. This work is made together with a company, Plus Italia. Plus Italia is an European leader in the design and manufacturing of fittings for pipeline of water and gas distribution. Its headquarters is in Brolo in Messina. The aim of our study is to specify a design strategy to avoid leakage on flange joint coupling. Because we have a flange joint with different material, because we have the stub made with polyethylene 100 and the flange made in steel. So we have the coupling between different materials, and also the changing over the time of the mechanical properties of the polyethylene, and also a possible fatigue effect due to the changing of the working pressure condition of the pipeline, for example, ram-8, that can affect the property of the pipeline and also of the flange joint. So the design strategy had to state the flange geometry and also the bulk retention. Today I will focus on flange geometry. There are a lot of reference standards that tell us how to design a flange joint, but no one of these standards tell us how to design a flange joint with mixed material. So there is the problem of how to design this mechanical coupling. In the first part of our study, we carry out a monoaxial traction test according to the standard UNI EN 572 part 2, using a dog bone 1A type specimen and using a free speed rate 1 mm per minute, 5 mm per minute and 15 mm per minute. We carry out our test with 4 types of polyethylene provided by 4 different manufacturers: Eltex, Borsafe, Ostalen and Sabic Wesselen. We use a test machine Ital Sigma 25 kN. Each set of specimens per manufacturer is composed by 11 specimens. 4 tests were carried out at 1 mm per minute, 3 tests at 5 mm per minute, and 4 tests at 15 mm per minute. In this table there are the test results, where we can see the different speed rate and value we obtain of the Young modulus and the yield stress. A set of tests was conducted at the laboratory of the University of Messina, the other one at the Plus Italia laboratory. As we can see from the green cell, we have the value according to the specific data provided by the data sheet of the manufacturer. Some manufacturers provide the standards that used to make the test. Someone else, like Ostalen, didn't provide any details about the test, how the test was conducted. From literature, we have a Young modulus of 1000 megapascal and a yielding stress of 23 megapascal. As we can see from these charts, the higher the speed rate, the higher the value of the Young modulus and the yield stress. this for all the four manufacturers. Here we have a comparison between the literature data of the young modulus and the experimental young modulus we have found in our experimental test. How we can see, there is an appreciable data scattering between the value. The same with the yield stress. In the second part of our numerical model, a finite element static analysis was conducted using ANSYS PDL. We realized an entire model with parametric geometry, mesh, material properties, and also of the external load well parameterized, like fluid pressure load and bulk pretension. We use several types of finite element, like solid 186 for modeling the stub and the flange solid part, the team 188 for model the bolt, the contact 174 and the target 170 for model the contact zone between the stub and flange stub contact. And at the end, the Bretons 179 to model the bulk pretension. No gasket was modeled at the stub interface. Regarding the boundary condition, we take advantage of the axial symmetry of our structure. So we apply fluid pressure of 13 bar applied to the internal pipe surface in order to simulate the ground behavior. We fixed the diameter radial translation of the other diameter pipe, and also we fixed the bottom face node of the external pipe, and then we applied a preload of 1 kilonewton. Then we made a convergence test controlling ANSYS using MATLAB. We used the young modulus provided from literature data. The convergence test was carried out on the external node of the stub surface, and we analyzed the radial translation, the von Mises equivalent express. We carried out a total number of 9 iterations, and for a reasonable computing time, we use a mesh of 3,153 elements, with a computational time of about 20 seconds in order to reduce the computational time of the overall iteration procedure. Later, a sensitivity analysis of 3 geometric parameters were conducted as suggested by the Plastitalia technician, in order to investigate the influence of the geometry parameters in the behavior of the model. We analyzed the radial translation, the axial translation, and the equivalent express. As we can see, for the flange 8, that ranged from 48.5 to 16.5 millimeters, we have no appreciable variation of this of the radial axial displacement and the equivalent von Mises stress. The same with the flange white, that ranged from 15 millimeters to 13 millimeters. While for the stub white, we can appreciate an increment of the radial and axial displacement, increasing the width of the stub and a decrease of the yield of the equivalent stress in the stub. is there's a comparison between the distribution of the von Mises stress in the stub of the flange at different value of y. At the end, sensitivity analysis of the different polyethylene provided by the different manufacturers were conducted, and there is no significant difference in the general behavior of our model. So, in conclusion, mechanical properties of polyethylene from different manufacturers were investigated and compared with literature data. A parametric finite element model of the flange joint was developed, and a sensitivity analysis of some geometric parameters was conducted in order to establish the influence of the geometry of distress, the influence of the geometry on the distribution of stress and displacement over the flange. And at the end, a sensitivity analysis of the polyethylene from different manufacturers was conducted, showing no difference between the different manufacturers of polyethylene. Further study will include an investigation on mechanical properties of aged polyethylene 100 in order to establish over the time the behavior of the flange joint, an investigation of the fatigue behavior of the same material, and also a study of the optimal geometric configuration of the flange joints by means of an optimization algorithm, and also a study of the pretension of the board. Thank you for your attention.